Recording is rolling. Today's Thursday, August 25th. So we're gonna start with these three starter questions here. Involves this guy throwing a ball straight up. Then we're gonna pick up where we left off yesterday with some textbook problems. And I do have an activity lined up, but we're probably gonna bump that to tomorrow. So take time here. All right, so you guys see this guy throwing this ball straight up in the air. Suppose you know the speed that you can throw straight up. Hey, I wonder what's the maximum height that the ball is going to reach. There's a couple of ball questions, but I think that one's pretty straightforward. So see if you guys can solve that. You know what you're doing, go ahead. If you're totally stuck, then I will throw you some hints. So this is definitely linear motion, just like up and down. Oh yeah, guys. 90 meters. Ooh. Okay, I think you're on the right track. That's not exactly the answer I'm looking for, though. The number shows up somewhere partway in the solution. Oh, see, this guy is throwing the ball upward, but which way is gravity pulling? Down. Ooh. So do you think your equation is just going to be a negative sign somewhere in there? Because there's opposing directions, right? Throwing up, gravity pulls down. Hey, to solve any linear motion problem, how many pieces of information minimum do you have to have? Three, right? Can you guys spot three pieces of information you have? I mean, there's one that's explicitly given, which is 30 meters per second. You could call that initial velocity. Maybe. What's like another couple pieces of information that maybe I didn't exactly give you? What do you say?
The initial velocity.
Okay, so you have initial velocity.
You assume the final velocity is going to be 0.
Yeah, guys, maximum height. What is the velocity of the ball right at the very top? 0. Yeah, all right. So got that. So there should be something else. What's the last thing you know? Yeah, Ty?
Is it acceleration?
Acceleration. Because gravity is pulling down about 10 meters per second squared as long as you're on Earth. Yeah. If you're not specified what planet you're on, go ahead and assume that you're on Earth. Right? That's implied. You'd be on Earth, right? If you put that guy on Mars, the answer to that would change. So. All right, how about now? Who knows the answer now? Yeah, Scott. 45 meters. 45 meters. All right. You guys are getting this bit by bit. All right. So, which of those kinematic equations did you guys use? First, second, or third? Yeah, definitely the third one. Now you could use a combination of the first two. Here's like the long way you could have done it. You could have shopped the second equation. You would have that's equal to 0 check, that's equal to 30 meters per second check, that's equal to negative 10 meters per second squared check. Solve for time, take that time, plug in the top one, and solve for x that way. But yeah, you're right. The fast way is just go straight to this third one. Notice I did not mention like how much time the ball is in the air. There is some amount of time that's not mentioned. So, and I'm not asking for it. So that's another hint that maybe that third one. Right. So we're gonna go final velocity squared equals initial velocity squared plus 2ax. And I can sort of modify this. Right? Say, well, final velocity squared equals initial velocity squared plus we have a special kind of acceleration called gravity field and a special kind of displacement called maybe like a height change. And we're solving for h max. Right? Now at h max, you guys said that what's this number equal to again? 0 meters per second for h max, right? So those two go hand in hand, right? And we're solving for this h max. Right, so let's go ahead and you know what I do? You know what I do? Right, you guys see this next question? What is h max for any throwing speed? Solve in terms of variables. let me do this. I'm gonna split this paper right here. And we'll answer the first two questions, one where you know the throwing speed, and the second would be like, well, what would be for any throwing speed? Okay. So in terms of variables, we got now 0 is equal to v naught squared plus 2gh max. That's in terms of variables. And if you start popping in numbers, besides the 0, it's already there. We know this guy was thrown at 30 meters per second. Okay. Oh, now I have to think about directions. If I define up as positive, I can leave that number as positive, square that. Then I'll call G a negative number 2, negative 10 meters per second squared, and then H max solve for. I should have gone landscape with this paper. So, but, yeah. You guys get that? Okay. So left of this line is in terms of variables, and then on the right side, just plug in the numbers. That's it. Oh, yeah.
Is G always gonna be -10 on Earth?
So will G always be negative 10 meters per second squared? Okay, so as long as you're on Earth, the true value on Earth more precisely is 9.8 meters per second squared. More often than not, I'll round it to 10 meters per second squared. AP does the same thing. And then should it be positive or negative? Well, that depends on which way you define as the positive direction. Actually, I'm glad you asked that too, because I want to make a point about that. Did you guys remember yesterday I did tell you have to be a little tricky with this particular formula, because if you square a number, you lose the negative information. See, if I turn this around, if I said, well, say down is positive, I call this positive 10 meters per second squared, and I slap the negative on the 30 instead, well, I would immediately lose that information because you square it. So you have to be a little tricky, a little careful with that. All right, so let's finish off this algebraically. 2 algebra steps I can solve both these. So subtract over the v naught squared. So negative v naught squared is equal to 2gh max. And then on the right side, do the same step. So 900 subtracted over negative 900, that'd be meters squared per second squared, equals negative 20 h max. Okay. All right, guys, all right. And so the left side I'm doing in terms of variables to get any solution. On the right side, I'm plugging in specifically this one guy's throwing speed. Okay. Oh, just for reference, 30 meters per second is approximately 67 miles an hour. So, and then the other algebra step is to divide by this 2g. Okay, divide the 2g down. So negative v naught squared on 2g equals h max. Or divide this down exactly what you guys saw myself, 45 meters. Okay. 45 meters per the guy who can throw it 30 meters per second. Great. Now, if you suppose this particular question is asked in like some physics textbook, maybe some college physics textbook, right? You see if the solution worked out. There may or may not be a negative attached right here, because you could define G to be positive either down or up, or you could assign negative value either way. Okay. Or they might just be looking at magnitudes of numbers. Okay. So the way I boxed it here, you have to plug in a negative value for G, and then the two negatives cancel out so that you get like a positive high value. Okay. You guys get that? Okay, good so far? Okay, so
Negative do not being squared though.
okay. So the v naught itself is being squared. The square, guys, does the square apply to the negative? No. So the square only applies to the v naught, and then the negative is after the fact. Okay. Now, if I group this in parentheses, yeah, that then would apply. But yeah, we run into this situation where you would lose that information. All right. There's one more question. So the first two questions are framed in terms of like if you know how fast you can throw. Okay, I gave you a specific number, and I said, well, what is it for any speed? And then now we have a way to find for anybody's throwing speed, how high they can throw the ball. You might be more interested in, hey, I wonder how fast I can throw a ball. Okay, it might be really easy actually to see how high it goes. Maybe you go next to like a multi-story building to see like what window does the ball go up to. Oh, and that's how the last question is framed. So given any particular maximum height, can you guys back solve how fast you had to have thrown the ball to get up to that height? Can you guys do that? Go ahead and do that. that would be in terms of variables, right? Right. So you and some friends get together, everybody's throwing a ball up next to a multi-story building. Oh man, right. So and so got it all the way up to like the 6-story window. Whoa. You guys kind of estimate how many meters that is. Like, now we can figure out how fast that guy can throw. Okay, you figured it out. Oh, yeah, what'd you get?
The square root of VF squared minus 2AF.
Okay. And then if you plug in 0 for VF,
Right.
that would give you
Square root of negative 2AF.
like square root of negative 2a, the square root, here, you got it right. Okay, let's do this. Okay. So we can start with the same place. Actually, we could pick up from this one if we wanted to. Maybe I'll go back to the original. Okay. VF squared equals V naught squared plus 2ax. I can modify that 2gh max. Okay. But if it's h max, then I know this number is going to 0. So that's just getting 0 squared is 0. Okay. But this time we're solving for what is the throwing speed. Okay. So when you take the 2gh and subtract that over, so the throwing speed squared equals negative 2gh max. Throwing speed is the square root of that. Okay. So you say, okay, look like that guy threw up so many meters. And multiply by gravity. Oh, oops, I forgot my negative sign. You know what though? Here. If I throw in a negative sign there. So it looks like the way if you throw it upwards, but gravity's pulling downwards, you guys see the two negatives are always gonna cancel. So if you plug in absolute values, you can in general say speed is proportional to square root 2gh, right? Or equal to square root 2gh. Actually, I want to solve a very similar problem. Be sure you guys are following this. Okay? So you guys know that you and your friends can get together. You can see how high the ball goes, and you can figure out everybody's throwing speed, right? You guys get that idea? Let's try it for what if you happen to throw it 45 meters? What's the square root of 2 by 10 by 45 meters? Okay. Square root of 2 by 10 by 45 meters. Hey, that's 30 meters per second, which was exactly the conditions for the very first question. Right? There you go. Just solved it the other way. I told you guys the Galileo story, right? So we're going back to 1589. This is like the dawn of modern science. Okay? People are just starting to think, hey, maybe we should, instead of like sitting around and applying armchair logic to the world, maybe we should actually go out and try this stuff and do some experimentation. Galileo runs to the top of the Leaning Tower, stretches out his very long arms, and drops different objects, different weights. He drops this guy, he drops this guy. Just saw people standing around. Throw him away. What do you think most people thought was going to hit the ground first? Yeah,
Heavier.
yeah. Most people thought the heavier one, right? Because Aristotle, back 2,000 years before, said, "Oh, well, heavier one, faster than light objects." But Galileo said, "Hey, I'm going to actually try this out." And what do you think the actual answer was? Think they hit the ground at the same time? Okay, so regardless of mass, you guys kind of proved that already with those cars rolling down. Okay? The mass didn't matter, didn't affect the motion. Okay? And so, hey, I wonder what that crash speed is. Call that V sub F. Okay. Can you guys solve for that crash speed? Go ahead and do it. What's that crash speed in terms of the height of the tower? Let's say you know that. Let's say height. You know how tall the Leaning Tower is. I'll call it H. So gravity field G. What is this crash speed right here? In terms of the height of that Leaning Tower. Oh, architectural fancy. What is the crash speed based on the height of the tower? If you know the height of the tower, how fast is everything crash landing? And who figured it out? Yeah, what you got right now?
I got the square root of 2 times the gravitational accelerator times time.
square root 2gh. You got square root 2gh. Hey, doesn't that look a lot like the answer to the last one? Throwing the ball straight up? Because it's almost the same question, isn't it? It's just turned around. Yeah. Let's use the exact same formula. Right? So crash speed squared equals drop speed squared plus 2g height of the tower. Let's call down positive. Well, if down is positive, gravity is positive. The motion of the ball is going into the positive territory. Now, Galileo's probably not chucking everything down, it's just dropping it from rest. This number goes to 0. And then maybe for second squared. Okay, we're solving for this one algebra step, square root both sides. Yeah, the crash speed is square root 2gh. Right? And all the numbers are positive because down is the positive direction. Just like those this fall on cliff questions we were doing. You guys get that? Guys, all right. All right, so what's it got lined up here? Gonna solve some textbook problems. Might have taken the first class to do that, but we'll see how the time plays out. You guys remember here? Just to remind you guys, your college textbook problems, which I assigned you some of these, and I'm gonna solve some other ones. Those are due next Friday, so Friday week from now. And don't forget, also you have a Unit 1 progress check that's been open for a while. Tuesday coming back from Labor Day. I actually have it set due like 8 o'clock in the morning on that day. So because I want to cover with you guys after you do it. I do have a projectile motion files lined up, and I'm gonna get probably on Monday. I think it'll be a good day to put those in your hands. But those are on Google Classroom if you wanted to look ahead a little bit, because projectile motion is like the other half of kinematic motion. And so we're kind of focused on linear right now. I'm gonna solve some linear. Okay, so okay, got this file. Got yesterday we did. I know we did the first 4 warm-up problems. Okay, I have to do this number 6 with you guys. I had lined up one to go over. Right, so might just do this one vertically, or sorry, verbally. But this figure shows a strobe photographs taken of a disc moving from left to right under different conditions. The time interval between each image is constant. So maybe we've got a disc moving left to right, and we've got a like camera tape, snap, 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 right? So equal interval of times. Taking the right direction to be positive, describe the motion of the disc in each case. So maybe in terms of velocity and acceleration. Okay? So the first figure, the disc is moving left to right. Which direction is its velocity? The positive direction, right? Because to the right would be positive direction. Which way is the acceleration of that disc? Positive or negative?
Negative.
Negative. Ah. There you go. You're right. Because you guys remember, if something has positive velocity but negative acceleration, that's slowing down. You guys remember that? Okay. How about this one? Which way is its velocity? Yeah, constant velocity. Okay, it's actually all 3 of these we're going to say positive velocity because they're all moving left to right. Constant velocity, which means its acceleration is what?
0.
0. Yeah, guys, constant velocity and 0 acceleration. Are those exactly the same? Are those synonyms? Yeah, those are exactly the same. If you say constant velocity, if you say it's 0 acceleration, those are identical scenarios in physics. Okay. And then how about this last one? Got positive velocity left to right, but what's the acceleration? Also positive. Because you see it's like speeding up in the forward direction. Let's look at this warm-up number 9. Consider the following combinations of signs and values for velocity and acceleration of the particle one-dimensional x-axis. Okay, so very similar to what we just been doing. Say if you have positive velocity, positive acceleration. Well, that is the last scenario we were just looking at, right? See positive velocity, negative acceleration. Well, that's this first scenario up here, right? We're breaking to a stop. Positive velocity, 0 acceleration. Isn't that just this middle one? Right? Just constant velocity. Okay. Anything that's negative velocity means it's like in reverse. Like you throw your car in reverse. Okay. How about hey, negative velocity but positive acceleration. So your car is in reverse, right? You're going backwards. But are you speeding up or slowing down? Slowing down, right? Because your car is tending forward even though it's going backwards. Right? Slowing down. Negative, negative, your car is speeding up in reverse. Negative velocity, zero acceleration, what's your car doing? Constant velocity, but in reverse, right? Ooh, what about this? What if you have zero velocity, but you also have acceleration? What is the car doing?
Going down.
Changing direction.
Changing direction. Yeah, actually, maybe the car is not a very good story to match with this. Maybe throwing a ball straight up in the air, right? Because if the ball at maximum height would have zero velocity, but it would also be under the influence of gravity, right? Could be a good example. Okay. All right. Okay. Next. Let's skip over to this one right here. Okay, so all these problems, some of them I picked out I want to do in class, and some of them I assigned to you guys. And there's a few extra ones too if you need extra practice. Right? Plus, you have all those other extra practice problems too. Okay, from talking about what's that page? You guys also have all these extra practice problems. You guys remember those? So lots of practice problems. All right, number 6, got a graph of position versus time for some particle moving along the x-axis. Right? Now, so is this still a one-dimensional motion pace? Yeah, all the particle is doing is go like forwards and backwards. Okay. Notice they gave us position versus time. So I wonder what velocity versus time looks like, or find the average velocity from 0 to 2 seconds, 0 to 4 seconds, 2 to 4 seconds. Right. So there's a bunch of questions that deal with average velocity. Now, average velocity we almost never talk about in this class, right? Like all those equations up there are all instantaneous velocities. Instantaneous, like what's going on like at that very moment. Average is like, well, there's some total distance and some total time, and so you divide the two. Right? But let's knock out at least a couple of these. Okay? So option A, so 0 to 2 seconds. So I've got time and seconds. So I'm going to put the first 4 seconds of the story on here. We'll just solve it at that point. 0, 1, 2, 3, 4. This goes up, okay, x in meters, goes up to the 10-meter mark. Okay. And then goes down to 6 meters by 2 seconds later. It's kind of like this, right? Okay. And then, well, the rest of the story goes like 0, 0, 0, something like that. All right, so 0 to 2 seconds, what's the average velocity? Okay. So do you guys remember what symbol we've been using for average velocity? It's V with a what on it?
Line.
Yeah, a little bar on it. So V bar. Yeah. Okay, so that's average velocity. So could you do like change in location over the time interval? Okay, that's like the definition of average velocity, right? Okay. So change in location. So that's 10 meters minus 0 meters. We're just doing rise over run. You guys yes. Over 2 seconds minus 0 seconds. Right. Change the y over change in x kind of do. But it's x of t. You guys see that's a change in 10 meters in 2 seconds, which is called 5 meters per second. You see that? Now, actually, that looks I mean that's just a straight line from during the first 2 seconds. Is that 5 meters per second also the instantaneous velocity every single moment for the first 2 seconds? Yeah, because that's the slope of the line everywhere for the first 2 seconds. You guys see that? Okay. So even though the question is average velocity, that also answers instantaneous velocity anytime during the first 2 seconds, right? What's the instantaneous velocity at the first second? Well, it's just like right about here. Okay. So still 5 meters per second. That's still the slope of that line. Okay, rise over run. Okay. But what about the next question though? Next question says from 0 to 4 seconds. Now, if you go 0 to 4 seconds, that's from this point to this point. Here's your 0 to 4 seconds. You see that? Okay. So the slope of that would be your average velocity. during the first 4 seconds. Okay? So V bar during the first 4 seconds, we got 6 meters minus 0 meters over 4 seconds minus 0 seconds. That's like 6 meters and 4 seconds, which is 1.5 meters per second. Right? Is that? Actually, it looks like what happened is someone was like walking forwards and then started slowly walking backwards. Right? But total displacement over total time. Okay, I should say displacement, not distance for this one, right? Because the distance would be really far. It'd be like this 10 meters plus the 4 meters back. Right? The displacement's only 6 meters. Yeah.
Is this, 4 is at 5 meters? Like,
Oh,
the 4
is that-
seconds on the graph?
Yeah, I think on the.
Oh.
it's supposed to be
Yeah.
fine.
Yeah, you guys are right. Oops. Okay, yeah, it does go down to 5 meters. I did miss that. Okay, so then if you did 5 meters here, it'd be 5 over 4 would be like 1.25. Okay, all right, there you go. So I guess my graph is slightly different, but you guys are right. Okay, and then right, so you guys get that idea. Number 17. It refers to the exact same graph, but it asks for instantaneous values. So number 6 and number 17 refer to the same graph, but this one's asking average, this one's asking instantaneous. Well, instantaneous, aren't you just like finding the slopes of the lines? Let's knock out one of these. No, let's do 2 because one of them we know already. Basically, option A or say question A says, what's the time? Or sorry, what's the speed right at the 1 second mark? Well, what right at the 1 second mark? Isn't that just the slope of this line? Which we already figured out, which is what 5 meters per second. Yeah, all right, so that's just the answer to that one, right? 5 meters per second. Hey, what about? I've got my own question. What about at the 2 second mark, like at this corner? Can you get an instantaneous velocity at a corner mark like that?
Zero.
Nah. Well, it'd be like something you just couldn't solve for. Right? So you just can't solve that. Although, yeah, you would be like turning around. I guess if you wanted to. Make it like physically, you could make a case for 0 because you say, well, maybe it's a really sharp turn, so it's like really sharp, like curve, and so there's like a 0 at some point. Okay. But notice they don't actually ask that question then. What about at the 3 second mark? At the 3 second mark, could you just do rise over run of this segment here and get the instantaneous velocity that way? Right? Okay. So yeah, I just want you guys to see that in principle you could do that. Next one, number 13. A person takes a trip. Oh, okay. I do like this one. Driving with a constant speed of this many kilometers per hour, except for a 22-minute rest stop if the person's average speed total is, well, look, their average speed is less than their instantaneous speed, right? How much time is spent on the trip and how far does the person travel? Ooh, right. So this question, we don't really care about those 3 kinematic equations or like speeding up, like, there's no acceleration we really care about. This is all just distance, speed, and time, isn't it? Okay. But I think it's going to lead to a system of equations. That's what it's going to be. So let's try this out. See if you guys can stay a step ahead of me. Set up some equations that could answer that, and then we'll go ahead and solve these. So, you know what's weird about this is they did mix and match all the units. Like we got kilometers per hour, and there's also 22 minutes. Let's convert the 22 minutes into hours, just so that everything's in the same unit. Right? Can you guys convert 22 minutes into hours? Let's do a little railroad trick. Showed you guys back about a week ago. Remember 60 minutes, 1 hour. 2 on 60. All right, so that's 0.367 hours. Okay, so we stop for that many hours, right? Okay, so we're going to use that number instead, just so that all the units are in kilometers and hours, right? So everything's consistent. Okay. Right, so we got here, person drives with a constant speed of 89.5 kilometers per hour. Okay. So I'll draw a little picture too. Okay. I like pictures. That was my thing, like visualize what's really going on. Okay, so we got this whole trip. Maybe this whole trip is like some distance x, right? And the only equation that everything's going to feed into, or I should say, the only formula is going to be some version of displacement equals velocity times time, right? Isn't everything just going to feed into that one way or another? Okay. So the whole trip, x, okay, we're going to do the travel speed times the amount of time traveled. Okay. So I'll go travel speed times the travel time. Right? Like if you only count the time that you're on the road, travel speed times travel time would give you the whole trip. Right? Or you could also say that if you do average speed, like v bar average speed, times the total trip time, right? That would also be the exact same distance. Guys, is this x, the same x? Yeah, they're the same x, right? But there's two different times we're considering, right? There's like just the time on the road, and there's also the complete time for the trip, which is longer, right? And the relationship between those two goes like this. The trip time is equal to the travel time that you're actually on the road, plus the 22 minutes. But I'm not going to say 22 minutes because when I start popping the numbers, it's just like T break. I do the T break because I have everything like in terms of variables. Okay, see, this is going to be one giant system of equations. Okay. Okay, so big picture here. Like why is the book asking this question, and what is it good for? So this is a non-accelerating situation. It's all just distance equals speed times time, or displacement equals velocity times time. Okay? Just going forward on this road trip. But this gets you to think critically about like how you would set up the system. I mean, that's like half the problem. It's like, can you set this up? Okay? I'm going to plug in some numbers. We'll make equations. We'll have a system of equations. Can you think critically about how you would set this up, and then further, can you solve a system of equations? Okay. I'm going to take this system of formula sort of, and turn the system of equations by popping in some numbers. They told you the driving speed was 89.5 kilometers per hour. That's like this right here. So the trip distance equals 89.5 kilometers per hour for, I'm going to say T. What do I want to solve for? They asked how much time is spent on the trip. Okay. So if they want to know the time on the trip, I'm going to do a little substitution here. Guys, can I take this third formula, rearrange it, and say that this travel time is equal to the trip time minus the break time? Can I do that? So all I'm doing is taking this one, gonna put this here. This one, I'm going to make an equation. This one, I'm going to make an equation. They're going to rearrange this a little bit. Okay. So this is going to be this travel time is equal to the total trip minus the break. Okay. So this is T trip, which they wanted you to solve for also, minus the break time. And the break time we have a number for. It's this many hours. Okay. We also have, in terms of averages, the average speed was, of course, slower because that includes the break. So it'd be 77.8 kilometers per hour, but just times the trip time. There's a little bit different ways to approach this thing, but see, I originally had like 3 equations, but I already substituted sort of the third one into the first one, so that just boils it down to 2. Okay. Oh, okay. Yeah. See how there's only 2 unknowns at this point? You don't know this x, and you also don't know the total trip time. You guys see that? Okay. Because if you have 2 unknowns and 2 equations, independent equations, I should say, it's not solvable. Yes, you can have one equation, one unknown, two equations, two unknowns, three equations, three unknowns. However many unknowns you have to have that number of equations to be able to solve it. Right. And the reason I started with three equations, because the other thing you wouldn't know is like the travel time that you were actually on the road. But I took care of that relationship and I already substituted that in. Okay. Guys see that? Okay. So we're just solving this. Yeah, and the student has exactly a good way to solve that. If this x is equal to this x, I can just take these two expressions and set them equal to each other because they're both the same x, and so both the same distance. Guys see that? So again, see if you guys can stay a step ahead of me. Beat me to the answer. Beat me to the answer. I'm gonna distribute this. Times 5. Okay, kilometers per hour times hours. That would just be straight kilometers, wouldn't it? Now by setting that equal to that, boom equals boom. Now I've got down to one unknown, so I can solve for the total trip time. Subtract this over, let's a good thing to do like in the middle of your steps too is make sure your units are working out. Like guys, kilometers per hour multiplied by some time, wouldn't that just give you some number of kilometers, like some distance? And can you add and subtract distances from each other? Kilometers minus kilometers, is that okay? Yeah, you can do that. But you can only add or subtract numbers that have the same unit. Last step, divide this down. Okay, so I'm getting this number. And that matches with this unit. Okay. Did you guys get that? You guys beat me to that? Okay, so again, big picture, this was basically a non-accelerating situation. And the critical thinking part was basically, can you set the system of equations and solve it? So once you got that set up, let's go ahead and solve it. Okay. Actually, this is only one of the answers because we still have to figure out what is x. I'm going to take this total trip time. I should be able to plug it into either one of these equations and get the same x, right? Okay. Let's see if I do. X equals some number of kilometers. Let's try it out. With 77.8 times this, I'm getting, here, get this way. X equals 219 kilometers, about rounding a little bit. Or if I plugged it into the top equation instead, what is 5 times 2.1 minus point, open parenthesis, I should say. 367. Yeah, it's the same distance. It's about 219 kilometers either way. Okay. Right, any questions on that one? All right, it's a good critical thinking question there. So we got lined up next. That was number 13. You know, one of the ones I did assign to you guys was number 20. There's only a few graph questions in here, but let me at least give you guys a hint on number 20. Number 20. Guys, what's on those axes? What versus time? It's the acceleration versus time, right? Now we put together a number of these like sets of graphs, like displacement versus time, velocity versus time, acceleration versus time. This is like that last graph, right? Okay. You guys tell me, what does the area of this rectangle represent? Change in velocity, right? Now, could you just look at this graph in isolation and know the starting speed? No, you have no idea what the starting speed is. Unless it says here in the setup, particle starts from rest. So that's nice. So they do have to explicitly tell you that it starts at 0 meters per second. Okay. You guys just told me, find the areas of these rectangles. Ooh, positive, negative. I bet they're going to subtract from each other, sort of, right? And figure out like some kind of change of velocity. But notice the follow-up question, because the question A is something about speed, velocity. Okay. But question B says the distance traveled. Oh, is that like another graph removed? You guys have to go from acceleration to velocity, and then here's the tricky part: velocity all the way back to displacement again. Okay. And in fact, if you have a constant acceleration, thinking 2 graphs removed from that, what is the x versus t graph going to look like? What shape? Some kind of parabola, right? Okay, so x versus t is going to be like a linear type relationship, and then what about 0 acceleration? Is here, but let's think what v versus t would look like. I bet v versus t is increasing at constant rate during the first was it 10 seconds? Then during these 5 seconds of 0 acceleration. 0 acceleration, does that mean the particle stops moving? No, that means the particle is what?
Not moving any faster.
Constant velocity. So constant velocity for a while. And then negative acceleration. That means the particle is going to do what? Slow down, right? Because it's moving forward, but negative acceleration. Then you get like a trapezoid looking v versus t curve. And do you think you could use that trapezoid looking v versus t curve to therefore solve displacement? Maybe something to do with like the area under that one, something like that. Okay. Guys get that? All right. But next one I'm doing with you guys is 22. What was that? The average person. See what was this one? The average person passes out at an acceleration of 7g. That is 7 times the gravity of Earth. Okay, because the gravity field we're all in right now, like if I drop this pen, that's just you could say 10 meters per second squared. You could also call that 1g. Right? Like what you guys ever heard like g force or something? Not really a force, actually acceleration caused by a force. Okay. So 7g. Yeah, you guys ever been say like merry-go-round or amusement park ride and you like feel really heavy? Okay. I bet the G's are going up 2, 3, 4, 5g. Suppose the car is designed to accelerate at this rate. Now that's a crazy bonkers acceleration, by the way. That's oh yeah, obviously right there you would like pass out of that. Right? How much time would be required for the car to accelerate from rest to 60 miles per hour? Okay. That's a really conventional way to describe acceleration of a car, right? So 0 to 60, they give you a time, okay? 0 to 60, which really has something to do with the acceleration of the car. Okay? That car goes 0 to 60 in like 2.5 seconds. Okay? But we're going to see what is the time. Okay? So what is the 0 to 60 on this car to reach 7 G's, which would pretty much put you at the point of like passing out, because you'd feel 7 times as heavy as you normally do. Okay? Well, one thing I see is mixing matching units. Right? I see miles per hour here versus g. We know in terms of meters per second. Right? Actually, I'll give you guys another value of g also. Right? So Earth gravity, we're going to use this. We're going to use about 10 meters per second squared. Right? You guys know it's like 9.8, but we're going to use 10 more often than not. Right? Do you guys know what it is in U.S. customary units? Like about 32 feet per second squared. We're never going to use that, but you know, if you ever see that, you know, here and there, it'll pop up. But your physics classes usually stick to metric system. Okay? So the 60 miles an hour, you think we have to convert that to meters per second would be pretty good. Okay. Let's set ourselves up some railroad tracks. That's one of the reasons I picked this problem out, is just for dimensional analysis practice. Because actual AP questions, AP will never give you miles per hour. Right? AP always gives you either meters per second, you know, metric units, or they'll just do variables. Just say, what is this variable in terms of that variable? Okay. But let's get some dimensional analysis practice. 60 miles per hour. Let's convert this into meters per second. Okay. So handle the mile unit first. I know 1 mile is pretty close to 1.61 kilometers, or I think 1.62, something like that, kilometers. It's either 1.61, 1.62, it's really close. It's really close to the golden ratio. Okay. And then every kilometer has 1,000 meters in it. If you want to get the exact definition of exchange is like 1 inch is exactly defined as 2.54 centimeters. So if you wanted to get that granular, you could. But this will get us close enough. Okay, so I got meters in place. Bing, bing. Miles cancels up, and then hours. So 1 hour is 3,600 seconds. You can do that. Okay, so now we have meters per second. Sorry, all right, got meters per second. Let's see how many meters per second that is. What is 60 times 1.62 times 1,000 over 3,600? That's about 27 meters per second. Okay, so 60 miles an hour, same thing as 27 meters per second. Now, how much time? Well, let's have ourselves a little table here, a tax BV table. Okay. So you should know 3 of these things, right? What are the 3 things that you know? Yeah, you know the 2 velocities. This is 27 meters per second. This guy starts from rest, 0 meters per second. And you also know acceleration, 7g. Okay. Could you call that 70 meters per second squared? You guys can do that, right? Okay. And we want to solve for time. Which equation, first, second, or third, is going to handle that? Second, good call. Final velocity, initial velocity plus AT. Guy just goes to 0 anyway. 27 meters per second equals, we got 70 meters per second squared. That's 7 Earth G's times how much time? Divide that down, 1 algebra step. What is 27 over 70? Looking at about, 0.3 something seconds. Right, less than half a second. So if you had a car that went 0 to 60 in less than half a second, and you got in that car and rocket forward, you would be right on the verge of passing out. Oh yeah. Second times. Any questions so far today? All right. We got 1 day left this week. So Friday, I want to choose some activities that are gonna hopefully solidify stuff we've done so far. I do want to get you guys projectiles in your hands next week, I'm thinking. So that will be probably our main focus next week. Yeah, so all right, yeah, stay on top of your stuff and yeah, more fun times ahead.